All right, algebra students, this is section 2.8, which is on graphing inequalities in two variables. In order to succeed at this section, you are going to need to be very good at graphing regular linear inequations. The only difference between graphing inequations and what we're doing today is that these are going to be inequalities instead of equations. They'll have less than signs or greater than signs or less than or equal to or greater than or equal to signs instead of this equals sign that we have in this review problem. Like I said, I just want to make sure that we're good at graphing y equals 2x minus 4 before we move on. If I told you to graph this, what you would do is you'd go down to negative 4 on the y-axis, which would be right there. That's your y-intercept. And then your slope is 2, which as a fraction is 2 over 1. Remember, slope is rise over run, rise to run 1, rise to run 1, rise to run 1. And this would be our equation, y equals 2x minus 4. We also have recently talked about graphing equations from standard form. Standard form is ax plus by equals c. And that's what this one looks like here. Oops, this should be a y, not an x. So for this example, what I've instructed you guys to do is to make this little t-table with zeros in the corners. What the zeros indicate in the corners is that you plug in 0 for x, and you see what y needs to be to make it true. So if you plug in 0 for x, this goes away. You have 4y equals 15. You divide both sides by 4, and you get 3.75. Similarly, you're going to plug in 0 for y. Let's go ahead. You can have that back. You're going to plug in 0 for y. And when you plug in 0 for y, this one goes away, and you can figure out what value of x makes it true. That one's a little easier. That one would be 5. So then you would plot these 2 points. 0, 3.75 is up here, and 5, 0 would be over there, and you would connect them. And that is the graph for 3x plus 4y equals 15. So that was our review. The thing that's going to make this section new today is that it's not going to be an equal sign. It's going to be, like I said, an inequality sign, like a less than or a greater than sign. There are two differences to graphing equations, like we just did in this example, in these examples here, versus inequalities. Two differences. Number one, the style of the line that we're graphing. If our inequality is a less than or a greater than sign, we are going to use a dotted line instead of the solid line that we've always graphed with. And if our line is less than or equal to or greater than or equal to, we still will make it a solid line. So that is one difference for graphing inequalities. The second one is that we are going to shade solutions. What do I mean by that? Well, let's talk about what a graph actually represents. So this y equals 2x minus 4, this red graph here, every point along this line is a solution to this equation. It makes this equation a true statement. For example, 6, 8, I believe, is this point here. If you plug in 6, 2 times 6 is 12, and 12 minus 4 is 8. So 6, 8 does work. It's on this line. Anywhere on this line will make this a true statement. Anywhere not on the line will make this a false statement, will not work. So when you are graphing equations like we have tons of times, that line is saying, hey, this is where the solutions exist. Now, with inequalities, if this was like a greater than sign, it's not just limited to on this line where the solutions exist. It would be like an entire region of this graph would all work. And so what we do is we shade where those solutions are existing as if to indicate, hey, this is our solutions. Any point in this region would satisfy the inequality. So those are the two differences. You graph them just like you did here. You essentially pretend they are equal signs, and then you decide if your line should be solid or dotted, and then you shade the appropriate region. So what do I mean by solutions? I did kind of go over that in the last slide, but it's an ordered pair that makes your inequality true. Okay? It would not be a solution if it makes your inequality not true. Let's look at this example. Here's an inequality, 5x minus 3y is greater than 12. And at least one of these points is a solution to this inequality. Let's go ahead and see which one or ones are. So the point 6, negative 3, 6 is the x, negative 3 is the y. If you were to plug 6 in for x, that would be 30. And if you plug in negative 3 for y, that would be negative 3 times negative 3, which is positive 9. You get 39 here. And 39 is greater than 12, so that ordered pair is a solution to the inequality. However, if you plugged in something like 0, 2, you plug in 0 for x, this becomes 0. Plug in 2 for y, this is negative 6. 0 minus 6 is not greater than 12. So 0, 2 is not a solution. Negative 2, negative 1, if you plug in negative 2 for x, that would be negative 10 plus 3. If you plug in the negative 1 times negative 3, that would be positive 3. Negative 10 times, or negative 10 plus 3 is not greater than 12. And when you plug in this one, negative 15 minus 15 is also not greater than 12. So this is your solution, or this is a solution to this inequality. So when we graph these inequalities, I did kind of go over this. We have two different things that we have to do. We have to shade, and then if our inequality is less than or equal to, or greater than or equal to, we'll use the solid line. And if it's less than or greater than, we use a dashed line. So let's look at some examples. Here we have y is greater than negative 2x. Remember, you're going to pretend that this is an equal sign to get the line. So if this was an equal sign, you'd say, okay, there's no y-intercept, so it goes through the origin, or its y-intercept is 0. And its slope is negative 2, so you would go down 2 over 1, down 2 over 1, or you can go up 2 left 1. Now you have to decide if your line is solid or dotted. This is just simply greater than, so it's going to be a dotted line. Now step 2 is to shade the appropriate region. Now, the most common way to do this is to test a point and see if it works. Because if you test the point, let's test the point 5, 0. If that works, the whole region should be shaded. This whole area here should be shaded. And if it doesn't work, if it doesn't make a true statement, then this is the part that should be shaded. So let's go ahead and try this. If you plug in 5 for x, you would get negative 10. Is that greater than, this is 5, 0, so 0 is the y value. Is 0 greater than negative 10? Yes, it is. So then that's telling us that this whole side should be shaded. We could double down, make sure that we're accurate by testing a point over here, like negative 5, 0. If you plug in negative 5 here, this would be 10. Is 0 greater than 10? Well, no, it's not. So that does vouch for this idea that this point should not be shaded, therefore it's this side that should be. I'm going to tell you another way to think about which side to shade, and this is kind of a shortcut, but it only sometimes works. When does it work? Well, it works when y is alone and on the left. In our problem, anytime you're in y equals mx plus b, y is alone and on the left. So it happens a lot. But in this problem, y is alone and on the left. So if it's greater than or equal to, shade above it. And if it's less than or equal to, right, less than, you think below. That it should be intuitive. It should make sense. So in this problem, y is alone and on the left. Therefore, you should be shading above this line. And that's exactly what we did, right? Y is alone and on the left, shade above the line. So pick any point on the line and shade above it. That would be this region. Like I said, it doesn't always work, but when it does work, it's really nice. Let's go ahead and graph this one then. 5x minus 2y is less than or equal to 20. Remember, this is in standard form, and what I've instructed you guys to do when we are in standard form is to make this little t-table with zeros in the corners. If you plug in 0 for x, this goes away. And what value would make them equal to each other? Remember, we're pretending this is an equal sign. So what value would make them equal to each other? That would be negative 10. Now plug in 0 for y. Plugging in 0 for y would make this one go away. And we would come up with the x value of 4. So now let's go ahead and plot these 2 points, 0, negative 10. That would be down here. And 4, 0 would be there. We need to decide if this is a solid line or a dotted line, and it is a solid line because of the or equal to. So you just connect them like normal. In this problem, y is not alone and on the left. So do not try to use this trick here. Instead, what you're going to do is you are going to use a test point. And when I can, I love to use the test point of 0, 0. Super easy to use. I couldn't use it here because you cannot pick a test point on your actual line. But in this problem, 0, 0 is not on my line. So I'm just going to plug in 0 for x and 0 for y, which makes them both cancel out. And you get the statement 0 is less than or equal to 20. Is that true? Is 0 less than 20? Absolutely. So then this whole region that had 0, 0 in it is going to get shaded. I could verify it and make sure that I'm right. 7, 0 when I plug in should not be true because it's not in the shaded region. So if you plug in 7, you get 35. 35 is not less than 20. So 7, 0 should not have been shaded, should have been the other side. Let's go ahead and pause it here. Make sure that you guys go ahead and test it, and then we'll resume here and go over it together. So in this problem, y is greater than x. This is in slope-intercept form. We are pretending it's an equal sign. There's nothing being added or subtracted. So 0 is where I would start. And its slope is 1, so it's going to go up 1 over 1. Or we could go down 1, left 1. We have to decide if we want a solid line or a dotted line, and this would be a dotted line. And then it's a greater than sign, right? Y is alone and on the left, and it's greater than, so then we shade above it. I could also use a test point. I could use the test point like 0, 5. That's right there. If I plug in 0 for x and 5 for y, I get 5 is greater than 0. Is that true? It certainly is. Therefore, it should be shaded. Next example, x is greater than or equal to negative 2. This is kind of a callback. Let's see if you guys remembered how to do this. What I instructed you guys to do when you have just x equals a number or y equals a number is to make a t-table. We know that the x, remember we're pretending this is an equal sign. So the only thing we know is that the x value is negative 2. We know nothing about the y value. It's not listed at all. So you can pick any y value you want. The only thing that matters is that the x value equals negative 2. Let's go ahead and plot these points. I can see now that it's a vertical line. It should be a solid line because of the or equal to. And then we have to decide which region to shade. Because it says x is greater than or equal to, that would be this direction. Right, these are the values where x is greater than negative 2. Like here the x value is 5, that's greater than negative 2. Here the x value is 1, that's greater than negative 2. So this would be the region I would shade. We have 2 problems left. One variety is using the graphing of absolute value functions that we just talked about last section. Remember, this plus 3 at the end is going to shift us up 3. And the minus 2 inside the absolute value signs, I would think would shift left to right. I would think would shift, minus 2 would shift left, but it actually shifts right 2. So you're going to go up 3 and to the right 2, and that's where your dot, that's where your vertex is going to exist. And then the number in front of your absolute value sign, that is your slope of your branches. Since there's no number there, it's just going to be 1. And this will be a dotted line because of the inequality. It says greater than, not greater than or equal to, for example. And then in this example, y is alone and on the left. And it's greater than, so that means that you shade above. So inside the V shape is what would be shaded. The alternative would be this whole region, just so we're clear. That's not the region that should be shaded in this example because it's greater than says shade above. The last thing I want to talk about is a word problem. This word problem says you are ordering pizzas for a party. You have $250 and you know that medium pizzas cost $14 and large pizzas cost $18. Write an inequality that describes this situation. Well, we know that we have a total of $250 and every medium pizza costs $14. We don't know how many medium pizzas we are ordering. Same thing with large pizzas. Large pizzas cost $18, and we don't know how many large pizzas that we are ordering, but we do know that we cannot exceed $250. Sounds like we could spend up to it, so we could spend the or equal to, but we can't spend more than $250. So that's what this statement would say. This is kind of an introduction to future important difficult lessons. So hopefully you guys can process through this inequality like this and see similar ones and do this. $250 is the total that we have. We have to make sure that we stay under that total. $14 for every medium, $18 for every large, and this would be the inequality. Let me know what questions you guys might have.